How much heat is needed to raise the temperature of a system from 20 degrees Celsius to 25 degrees Celsius if the heat capacity of the system is 8 times 10 squared joules per Kelvin? As long as no chemical or phase changes are happening, the amount of heat flow, which is often represented by the letter Q, is directly proportional to the temperature change. Mathematically, that means that the ratio of the two quantities is a constant. If we take the ratio of Q to delta T, the proportionality constant is called the heat capacity, C. When we say the two quantities are directly proportional, we mean that if Q is 0, delta T is 0. Obviously, if there is no heat flow, we do not expect a temperature change. And if the amount of Q changes, the change in temperature also changes by the same factor. For example, if we put in twice as much heat, we expect the temperature change to be twice as large. Let's examine what we're given in this problem. We are given the heat capacity. We are also given the initial and final temperature, so we can calculate the temperature difference. And we are asked for the amount of heat flow. Therefore, we just need to rearrange this equation to solve for Q. Q equals C times delta T, the amount of heat flow, is equal to the amount of heat for every degree change in temperature, times the actual change in temperature. 25 degrees Celsius minus 20 degrees Celsius is equal to 5 degrees Celsius. Note that 1 degree change on the Celsius scale is equivalent to a change of 1 Kelvin. So our delta T is 5 Kelvin. Carrying out the indicated calculation gives us a value of 4 times 10 cubed joules for Q. Note that we only keep 2 significant digits in the answer. Because our less precise factor has only 2 significant digits. Therefore, the correct answer is C. Let's see if the answer makes sense. It takes 800 joules to raise the temperature by 1 degree. It should take 5 times more heat to raise the temperature by 5 degrees. 5 times 800 equals 4,000. Note that the formula we use in our calculation is, strictly speaking, just an approximation. In reality, heat capacity depends on temperature. So the proper mathematical procedure for calculating Q is to integrate heat capacity versus temperature from the initial to the final temperature as shown in this equation. In most cases, we only deal with small temperature changes where the heat capacity can be safely assumed to be constant, and the formula we used works fine.